Okay, hi everybody. We're going to go ahead and go over each and every one of these questions on here so that you can be prepared for Thursday's test. So, in this question, which of the following molecules is predicted to have the greatest molecular dipole moment? Okay, so it's asking for the molecule, all right? And so you're looking for one that will obviously be polar. And so you have to be able to draw out something like all of these. And so hopefully you've by now started to get pretty good at it. So the carbon dioxide, when you draw it out, should come out something like, and this actually has a dipoles that cancel, so you have a zero dipole moment. And then you have H bonded to Br, and that should have a relatively high dipole. It's practically ionic with a nonmetal and a metal. It's actually considered to be two nonmetals because that's the way H is behaving. But the difference in electron negativity in both cases are both considered to be high. So we're going to have to compare in all three of these which one is likely to have the greatest difference in electron negativity. Please remember electron negativity goes down the group, and if you have it decreasing down a group, then that means that your only correct answer would have to be the one with the highest electron negativity, knowing that hydrogen has a pretty low electron negativity. So we would have to say that in fact C is our correct answer here. All right. The next one, 2, 3, 4, it looks like the next three questions. Consider the chemical bonds found in solid sodium hydrogen carbonate. So we're talking about sodium hydrogen carbonate. For each bond specified, choose the best description. Okay, so we have choices of A, ionic bond, B, hydrogen bond, C, single covalent bond, D, double covalent bond, and then resonant covalent bond. And let's make sure we know what we have here. So I have some sodium that is actually going to give away its electron to the hydrogen carbonate molecule. And so you end up with a hydrogen here, and the carbonate has a resonating structure that goes like this. So you end up with your oxygens like this, and oxygens like this. Okay, and so that's what you end up having there. So overall, they're asking about the different parts of this molecule. The carbon to oxygen bond. So the carbon to oxygen bond is representative of one of these three oxygens here. So it is very definitely a resonating bond. So that should be E. The sodium to hydrogen carbonate bond, and that would be a metal with a nonmetal polyatomic. So that is A, an ionic bond. And then number 4, the oxygen to hydrogen bond. Now you might be going, oh gosh, I don't have an oxygen to hydrogen bond. And it might be that this, I drew it wrong, and it might be that this is actually bonded to one of these right here. So you'd have to call that, because you will not have the situation where you can have anything, hydrogen to oxygen bond is not going to, is not going to do anything other than single bond. You could be tempted to call this a hydrogen bond. It is very definitely a single covalent bond, and hydrogen would never double bond, and it can't resonate either because it can't make a double bond. So our choice is really hydrogen bond or single covalent bond. Because they're talking about the hydrogen to oxygen bond, that actual physical bond, I think the best answer here is C. You can argue that between molecules of hydrogen carbonate, there would be hydrogen bonding, but within the molecule itself, there is not hydrogen bonding. It has to be, hydrogen bonding, remember, is a force of attraction between two different molecules. So those would be your correct answers there. All right, let's continue on. Number 5, consider the molecular geometries of linear bent, trigonal planar, trigonal bipyramidal, and octahedral. Which of these geometries is not represented by any of the geometries listed? So we end up with some drawing that we have to do. We're going to have BeF2, and this is the way this one comes out with all of these electrons here. Be is one of those that bonds with only 4 total electrons around it, so it's special, and so we'd have to call that one linear. So that one can be crossed out because linear is representative. So then we have BF3, and BF3 is also going to be a strange and one that only bonds in with 6 electrons around it. And that one's going to look like this. And trigonal planar is listed there. So we've got linear, we've got trigonal planar, so we get to cross that one out. And then we have CCl4, and CCl4 is going to have these 4 chlorines around it, just like this. And we know that that's 4 bonded pairs and 0 lone pairs, so that's tetrahedral. And if we go look at our list, we notice that there is no tetrahedral on the list. And so this is going to be our correct answer. Let's make sure that we know what the other 2 look like. Arsenic pentafluoride ends up looking like this, with 5 fluorines around it, just like this. And that is trigonal bipyramidal. And then when we do water, water ends up looking like this. And water, of course, makes a bent shape, so we can cross that off as well. Okay, there we go. Okay, questions 6 to 8 refer to the following diatomic species. Okay, which has the largest bond dissociation, bond breaking energy. Okay, and since this is in multiple choice format, you're not going to be able to look this information up. So you're going to have to figure it out based on all kinds of things. And one of those things might be the size of the atom. So Li2, B2, N2, O2, and F2, some of the things that you need to know is Li, let me make sure here, writing on it. Okay, so Li2, if we have that, we would have an Li bonded to an Li like that, and a B bonded to a B. And the N2, though, what you need to know is that when N2 bonds, it bonds like this. And just making sure boron is 3, so we end up with, yeah. And O2, I really dislike this question now that I'm looking at it. What it's trying to get you to do is bond these around each other like this, and it's using, my problem is with both of these here. However, we can still answer the question. It's having the question of which has the largest bond dissociation energy, and you would have to pick the one that has the triple bond, because it would take the most energy to break the triple bond. So that's going to be our correct answer, C, for that one. Which has a bond order of 2, that's going to be D for the oxygen, and which contains 1 sigma and 2 pi bonds, and that's going to go back to C, giving you sigma and pi bonds. These over here, you might be going, well, both of those are weird. One of them is a metalloid and one of them is a metal, and they just don't bond like that. And you're right. But I would have a hard time believing that I could make a double bond out of lithium having 3 total electrons and boron having 5 total electrons, and it just makes it difficult for me to believe double bond and so forth. So that's what we're looking at there. Okay, so for question number 9, we need to be able to answer the question, identify the molecules that have planar configurations, and that will be what you're looking for. So we need to make sure that we understand what is meant by that term, planar configurations. That literally is meaning that we are either talking about trigonal, planar, or linear reactions, all right, or molecules. So anything that is trigonal pyramidal or tetrahedral or a expanded octet are all not going to follow planar configurations. So we're going to have to be able to draw these all out. When we do BCl3, B and Al are both ones that bond with only 3 groups around them. So BCl3 looks like this, and BCl3 has a completed octet in 6, and that's why it's weird. But that very definitely is a trigonal planar one. So that one works. How about CHCl3? Well, that one's going to have 4 things bonded around it, so you will notice right away that that one has 3 Cl's and 1 H bonded around it, so it is very definitely a tetrahedral, so that one is not a good answer for planar. And then NCl3, so on that one I have 3 times 7 for the chlorine plus 5, so that's 21, 26. So I'm going to end up with Cl's around it like this. And then there will be a lone pair of electrons and it will go right there. So this one actually ends up being pyramidal. And since this one is pyramidal, that means that number 3 also gets crossed out. That means A is our correct answer here for the one that is planar only. Okay, going on to our next one. Our next example, number 12, which of the following molecules has a dipole moment of 0? So we're looking for the nonpolar molecule. So for each of these, we are going to have to figure out how they're written. The C6H6 is actually written as a, let me make sure that, I am not going to include one like C6H6 on your test because it is somewhat unfair, because it is an organic molecule that you don't know very much about. It is written like this, with each of these are C's right here. That's a C, that's a C, that's a C, that's a C, and that's a C, as is that. And then coming off of each C is an H, an H, an H, an H, an H, and an H. And so this one very definitely has no dipole. All of those bonds tend to cancel each other out. So that one is the no dipole. That one's going to be our answer. NO, does that have a dipole? That's 5 electrons plus 6 electrons. So we end up with oxygen next to it. So if we make them have a single bond, that means the nitrogen still has 3 and the oxygen has that left. So we can go ahead and double bond that. So if we double bonded that, then we would have this going on here, and then we would be wondering, well, what the heck are we going to do now? And so then we end up going, okay, well, what about if we triple bond this? So if we triple bond this, then we would end up with a triple bond here, and it's going to look weird, and it is. So it's going to end up looking like this, triple bond to the oxygen. That's going to look like this, and this is going to look like this. Or not even that, because it uses that 1 electron, so it's going to look like that. And it's weird, and it doesn't happen very often, but it's very definitely got a dipole going on there. So we would go on then and look at the SO2. S has 6 valence, O has 6 each, so 18 valence electrons total. So my S goes in the center. I have oxygens on either side, and if I have, was that 18 total? So right now, I have used up 16. So if I did that, I would go, okay, well, that's 16 electrons, but I don't have a completed octet. So I would need to have a resonance structure here. So I would end up with a double bond on this side and a single bond or a resonating structure on this side. But because of that lone pair of electrons, that one also has a dipole. So we get to cancel those out. We've already established A is our correct answer. NH3 actually is a pretty much more common one, and it will look like this. And so that is going to be a polar one as well. It's got a lone pair. How about H2S, which ends up looking a lot like H2O does, with the lone pairs of electrons like that, and that also has a dipole moment. So A was our correct answer there. All right, so then we go on to one like number 13, and number 13 is going to be one of those bond enthalpy types of things. So we have to figure out our bonding before we can figure out how to calculate it. So let's go ahead and write down our bonding real quick here before we go any further. There we go. There we go. Okay, so our bonding, I have an I to I single bond, plus I have 3 C to L single bonds, and then I have 2 I with a Cl3 around it. So we're going to have I with 3 Cl around it. All right, so if I count up these valence electrons, I've got 7 for iodine plus 3 times 7 for chlorine, so that's 28 total electrons. So right now I've used up, when I show all my valence, I've used up 24 total electrons, and this one is going to have an expanded octet, so it'll end up with lone pairs here and here. All right, but my bonds are going to be 3 I to Cl bonds times 2. Okay, so let's go ahead and write this into our equation. So we have an H, and remember it's going to be reactants minus products. So reactants minus products, I've got 1 I to I bond, so that's 149. And I'm going to add that to the other reactant, which is going to be 3 times Cl to Cl, 239. And that's going to be my reactants. And let's remind everybody, this was the I to I single bond, and this was the Cl to Cl single bond. From that, we're going to subtract, because remember, it's reactants minus products. Reactants minus products. And we're going to subtract the products. And the products are going to be 2 times 3, and it's the I to Cl bond. So this is the I to Cl bond. Whoops. And so that number is going to be 208. And there's what we have there. So now we just have to plug this into our calculator. So we have 149 plus 3 times 239. And then we're going to subtract from that 6 times 208. And we end up with negative 382 kilojoules. And B is our correct answer there. Okay, so another little bit of good practice for us there. If we had to answer if this was endothermic or exothermic, because that came out to negative, we would have to call that exothermic. Okay, so here we have these molecules here, and it's asking us which of the following does not describe any of the molecules, does not describe any of the molecules. So we need to be able to draw out all of those. CCl4 comes out like this, so that's going to be a tetrahedral, and we got tetrahedral already, so tetrahedral gets to be crossed off the list. Then I have CO2, and by this point in time, you ought to be going, okay, I know what CO2 is, there it is, and that's linear, so we get to cross off linear. And then I've got PCl3, and I have 3 Cl's, and I am going to end up with a lone pair here, so that's going to be trigonal pyramidal, and I get to cancel that one off. And then I go to PCl5, which is my P in the middle, and it's got 5 chlorines attached around it like this. And so that comes out to trigonal bipyramidal, and I don't see trigonal bipyramidal here, so that's going to be the one that is not on the list, but it's asking which of these does not describe anything that you have. So while that is not on the list, that is not one of my answer choices. So we're going to go on, and SF6 is going to look like this. We're going to have 6 F's around my six F's as in fluorine around my S sulfur, and that's actually going to be octahedral. That means that the only one that is not represented by any of those molecules is the square planar one. All right. Moving ourselves along, we are asking which of the following compounds is ionic and contains both sigma and pi covalent bonds. All right, so let's keep in mind that means that we are looking for a metal. So we need to have metals. Here's a metal, and here's a metal. everything else has only nonmetals, so I get to cross off B, C, and D. That means I need to be able to only look at what I have going on in FeOH3 and NaCN. And so when I look at FeOH3, I'm going to make the Fe3 plus molecule, and I'm going to have the O to H single bond here. And so that's actually what I have going on there. So this does not contain any pi bonds. So it must be this one down here, E. And so I would have Na1 plus bonding to C to N. And when I write out that Lewis structure, I end up with both sigma and pi bonds in here. And so that is where the idea of sigma and pi bonds come from. This one only has one sigma bond, whereas this one has one sigma and two pi bonds. So E is our correct answer here. All right, here we go. Number 16, which statements are correct about diamond, graphite, and C60 fullerene? All right, so you have to remember all the important facts here about those. The poorest electrical conductor of the three, we have to be able to remember that this is the diamond, and the diamond has no delocalized electrons. So that is a true statement. Atoms in graphene and C60 fullerene are sp2 hybridized. That is a correct statement because they made hexagons and pentagons. And those two shapes actually follow the sp2 hybridized. They also had some pi p orbital electrons that are the pi bonds, and those were the delocalized electrons. So that's where the other electrons are, and that is a true statement as well. So that one's true and that one's true. And then the atoms in diamond and C60 fullerene are arranged in hexagons, and this one is false because the diamond is actually arranged in tetrahedral shape, and that is not a hexagon. So the correct answer here should be 1 and 2 only. Okay, so we're on question number 17. Which statement about the bonding between carbon atoms is correct? In C60 fullerene, each carbon atom is covalently bonded to 3 other carbon atoms, and that is a true statement. That is because, remember please, that's true because what we have is sp2, and remember it's all made of carbons. Remember, this is allotropes of carbon. Then we have the C60 fullerene. Each atom of carbon is covalently bonded to 4 other carbon atoms. No, that's actually false. That would be diamond that we would be talking about there. And then in graphite, each carbon atom is covalently bonded to 4 other carbon atoms. Again, that would be diamond. And in graphite, each carbon atom forms a double covalent bond with 3 other carbon atoms. No, it does not. So we have that going on. It does form one double bond, but it does not form a double bond with 3 other carbon atoms. So A was our correct answer here. So those are facts about C60 fullerene, graphite, and diamond. So you do need to make sure you know those things as well. All right. We are on question number 18. What is the number of sigma and pi bonds and the hybridization of the carbon atom in this molecule? So you should say there are 1, 2, so let's count them off. Sigma bonds, 1, 2, 3, 4, 4 sigma, and 1 pi bond. There's a pi bond right here. And then it's asking what is the hybridization of the carbon atom. There are 3 bonding locations, so you have to call that sp2. All right, so for the next one, observe the Lewis structure of ethyl ethanoate. Predict the bond angle around the second carbon. So here is our second carbon. I would predict the bond angle would be 120 since there are 3 things bonded around it. And then the oxygen atom here, but you have to remember that the oxygen atom has 2 lone pairs here. So you would have to say that it is, I think that the accepted one that they would say is it would be definitely less than 109. Oftentimes this bent is actually 104.5. So there's that, and you do have to have your bond angles memorized for this as well. All right, then state and explain the relationship between the length and strength of the bonds between the second carbon atom and the two oxygen atoms in ethyl ethanoate. Okay, so the relationship between length and strength between the second carbon atom and the two oxygen atoms. So they're referring to this bond here as compared to this bond here. So to answer this question B, we would have to say that the C to O double bond is shorter, let's spell it right, but stronger than the C to O single bond. Okay, so basically double bonds are shorter and stronger than single bonds, and I think that would handle most of it right there for you. Okay, I think that we are close to being done here. Does that cover everything for us? Oh, almost done. Okay, so on this question, what is the Lewis dot structure for sulfur dioxide? Include its molecular shape, polarity, and hybridization. And so we have to be able to draw this effectively and identify all of those things. So we have sulfur dioxide, so you're going to have to say, oh, sulfur dioxide is SO2. I'm going to add up 6 plus 2 times 6, so I'm going to end up with 18 electrons. I'm going to have to put sulfur in the center, and then I am going to bond the oxygens around it just like this. And I'm going to go ahead and play with these electrons just a little bit. So right now I have used up a total of 18 electrons, but I noticed that there is not a full octet for the sulfur. So I am going to have to show a resonating structure here. So a double bond on one side and a dashed line representing the place for the resonating to occur. And then I'm going to go ahead and put this into brackets. Remember, brackets on a resonating structure are required. Molecular shape on this is bent. Polarity is definitely polar. And hybridization on this ends up being that there are 3 electron domains. So we end up with sp2 hybridization. All right, I think this might be our last question here. So let's go ahead and look at number 21. Oh, I'm wrong. There's not. I added more in here. So identify the IMFs of carbon dioxide, dihydrogen sulfide, and water, and arrange them in order from strongest force to weakest force. So it might be helpful to have these in Lewis structures. So we end up with C double bond O like this. And then I have dihydrogen sulfide, so that's S with 2 hydrogens, one on either side like this. And then I have water, and that's going to be like this. Okay, so there are my my examples there. This one is going to be completely nonpolar, so this is going to have only LDF forces. This one is these both are going to be polar, but this is going to be dipole forces, and this is going to be hydrogen bonding. And so we would be able to put this as strongest force to weakest. So water first, and then I would say dihydrogen sulfide, and then I would follow that up with CO2. Okay, just putting them in order. It does not say to explain why, it just says to place them in order of strongest to weakest. Okay, question number 22. Diamond, graphite, and C60 fullerene are 3 allotropes of carbon. Describe the structure of each allotrope. It does not say to draw it. It simply says to describe the structure of each one. And there are 3 points here. So diamond would be made of 4 carbon to carbon single bonds, making a tetrahedral macromolecule. And that is a way for you to say that it is a very large molecule. Macromolecule. There we go. I finally got it right. Then we could say graphite, made of 3 C to C, actually 2 C to C single bonds and 1 C to C double bond, in hexagonal shapes. Which arrange themselves in sheets. Okay, and then C60 fullerene, you would have to say that they are made up of both hexagonal and pentagonal or pentagons. With C to C single bonds and C to C double bonds. If you wanted to say that both of these had delocalized electrons, you could add that in, but I'm not sure that this question requires you to do that. You could say C60 fullerene makes a spherical shape. Okay? All right. And then I think maybe we're close to the end here. Compare the bonding in diamond and graphite and thus the properties of each. So diamond would have the electrons all trapped in single carbon-to-carbon single bonds, making a large tetrahedral shape, whereas graphite would have 2 single and 1 double bond with some electrons in the p orbital, and that p orbital ends up having or making a delocalized electron. So as a result, we would expect diamonds to be hard and have a high boiling point, but we would expect graphite to be much softer and having still a high boiling point, but would be much softer. And we would know that graphite ends up having the ability to be removed in sheets. Okay, everybody, that's going to be where we stand right there. Thank you.